Okay, so parabolas. And in this video, and actually I'm going to make two videos here, one both kind of short so that they upload to YouTube better. So we'll look at standard and general form of parabolas, the quadratic equation, complex numbers, factoring quadratic inequalities, and quadratic word problems. So the standard form for parabola is this, and we've seen this before because this is the form that we can use to move graphs around in. The values h and k here stand for the vertex. A is a stretching factor, and remember that if a is negative, we flip the graph over the x-axis. So use transformations to graph this function. So this is the graph of y equals x squared, and it's got three special points, 0, 0, 1, 1, and 1 minus 1. What's going on here? The plus 1, that means move left 1 unit. So these two points move to here, here, and here. The minus 2, flip and stretch by a factor of 2. So that means that these 3 points now that have been moved left 1 unit get flipped over the x-axis. This one's already on the x-axis, so it doesn't move any place. And then we get these 2 points. And then we stretch it by 2. That means we multiply the y-coordinates by 2, so this point doesn't move, but this point moves down to here, and this point moves down to here. So after the moving left and the flipping and the stretching, we have these 3 points. And then finally, add 3, that moves everything up 3. So this point moves up 3 units to here, and this moves up 3 units and ends up there, and this moves up 3 units and ends up there. So a parabola looks like that. And the vertex is right here. So the vertex is at the point minus 1, 3. This point is the vertex on y equals x squared, and moved left 1. Flipping and stretching doesn't change it, and then when it moved up 3. The axis of symmetry is the vertical line through the vertex. The parabola is symmetric over the axis of symmetry. So that's the line x equals minus 1. Y-intercept, that's here. It looks like it's 1. What do we do to find the y-intercept? We set x equal to 0, and that gives us y equals minus 2 times 0 plus 1 squared plus 3. So we set x equal to 0 in this equation to find the y-intercept, and that gives us y equals minus 2 plus 3 equals 1. So my y-intercept is x coordinate 0, y coordinate 1. That's this point. X coordinates, there's one there, and x-intercepts are there and there. What are the x coordinates of the x-intercepts? So to find the x-intercepts, set y equal to 0, solve for x. And so here we're dealing with y equals minus 2x, minus 2 times the quantity x plus 1 squared plus 3. To solve that for x, we're going to move the minus 3, the 3 over to the other side. It comes across as a minus sign. Divide both sides by minus 2. We get 3 halves on the left side. And that, and then we take the square root of both sides, remembering that our plus or minus gets, our square root of a number gets a plus or minus. And so, oops, x equals 1 plus or minus square root of 3 over 2. So our two x-intercepts then is 1 over here, and that's minus 1 minus square root of 3 over 2. And there's one here, oops, comma 0, that's that point. And there's one here, and that point is minus 1 plus square root of 3 over 2, comma 0. And notice that the x coordinate of the vertex, right, that's my minus 1, right? and the two x-intercepts are symmetric around the axis of symmetry there. So general form for a parabola is this: x squared plus bx plus c. You've probably seen that before. So we want to be able to graph parabolas by transformations. So we can turn this into standard form. Remember that standard form is a x minus h squared plus k, with hk being the vertex and a is the stretching factor. So to complete the square, to convert this parabola into this form, what do we do? Well, we start with y equals 2x squared minus 4x minus 3. When we're completing the square, we always do that with a coefficient of 1 on the x squared, if you remember the examples that we did before. So I'm going to divide both sides by 2. To get a coefficient of 1 on the x squared. So y over 2 equals x squared minus 2x minus 3 over 2. So we divide all the terms by 2. And now we've got a nice 1 as our coefficient of x squared. So we take the b term, the minus 2, divided by 2 and square it. And that gives me minus 1 squared, which equals 1. And we add this to both sides. That gives me y over 2 plus 1 equals x squared minus 2x plus 1 minus 3 halves. And as always, when we're completing the square, those three terms become our perfect square. And now I just solve for y at this point. Subtract a 1 from both sides. Right? And minus 3 halves minus 1 is minus 5 halves. And then multiply by 2. So what have we got here? We actually now have two different formulas for the same function. Right? This is the same function. No matter what x you plug in, you get the same y out, regardless of which formula you use. So we have two different formulas for the same function. This formula here that allows us to graph it pretty quickly because it's right 1 unit stretched by 2 and then down 5. So we start with these 3 points. Right 1 unit moves them to these 3 points, stretching by 2, leaves this one alone, but multiplies this by 2, which moves that up to a height of 2. Height of 1 goes up to a height of 2. And then those 3 points go down 5 units. Oops. 5 units will be way down here. And so there's my parabola. Right? So the vertex is down here. That's at 1 minus 5. The y-intercept, well, from the graph, we actually know that the y-intercept is right here, 0 minus 3. So where are the x-intercepts, right? One is here and one is here. And note that our axis of symmetry is right here. So the x-intercepts are symmetric around the axis of symmetry. So two ways to solve this. We could start with y equals 2x squared minus 4x minus 3 and use the quadratic formula. or we can start with y equals 2x minus 1 squared minus 5 and solve by using the standard form. In both cases, we start by setting y equal to 0. If you're interested in x-intercepts, we always set y equal to 0, and then we try and solve that. So solving this one here first, we add a 5 to both sides, divide both sides by 2 so that we can isolate the squared term, take the square root of both sides. We get 1 plus or minus square root of 5 over 2 equals x. And note again, this is our vertex is at 1, and our two x-intercepts, well, one is square root of 5 over 2. Right? We take 1 and we add square root of 5 over 2 to get that one. The other one is 1 minus square root of 5 over 2. We take 1 and we subtract off the distance square root of 5 over 2 to get my x-intercepts. 1 minute scrolling. There we go. This, incidentally, if you ever ask for the exact form, leave it as a square root. The decimal approximations for this are 2.58, that's the plus, and minus 0.58, that's the minus. So you may have seen the quadratic formula before. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So if we have an equation like this, we've got 0 on one side and a quadratic like that. When on the other side, we can use the quadratic formula to find the x-intercepts. And so that's 4 plus or minus the square root of 16, because that's b squared, minus 4 times 2, because that's a, times minus 3. And we have to be a little bit careful about our signs there. That's all over 2a. A here is 2, so it gives me 4. So x equals 4 over 4 plus or minus the square root of 16 minus, well, this is 8 times 3 is 24, but minus and minus is plus, so that's 16 plus 24. Let me undo that because I just got a little clogged. 16 plus 24 over 4. And that's 1 plus or minus the square root of 40 over 4. And with a little wrestling about with square roots, you can show that square root of 40 over 4 is the same thing as square root of 5 over 2. I'm not going to grind through that in particular detail. If this is the, if you're asked to solve this quadratic formula, this would be fine. Great, so that gives us the quadratic formula. And here, of course, is the equation for it. There's two parts of the quadratic formula. There's this fraction, and then there's this fraction. When we look at examples 2 and 3 above, what we got in both cases was that we had a parabola that had an axis of symmetry. An axis of symmetry and a parabola and an x-axis. So where were my, maybe the y-axis is over here somewhere. So where are the x-intercepts? Well, this line is x equals minus b over 2a. That's this part of the quadratic formula. And then you go a certain distance right and left. So you're adding and subtracting this thing. So this is the x coordinate of the vertex. And then this part here is where you're going left or right to find the intersection. So the vertex has x-coordinate h and y-coordinate f of h. And that makes it pretty easy to actually sketch graphs, right? Because the standard form is this, and you could complete the square on that, but we don't have to here. We know that the vertex has got an x-coordinate and a y-coordinate. The x-coordinate is minus b over 2a, which in this case, b is 4. So it's minus 4 over minus 2 times 1, because our a value is 1. Nope, no, that should be a 4. So it's minus 4 with the minus sign coming from that. And I don't know why I have a minus 2 there. It's just a minus 4 over 2 times 1, which is minus 2. So our x-coordinate of our vertex is minus 2. What's our y-coordinate? Well, you get the y-coordinate by plugging that into our function. So it's going to be minus 2 squared plus 4 times minus 2 plus 5. So y equals 4 minus 8 plus 5, y equals 1. So this is my vertex, is that point, right? We find the x-coordinate, and then we plug that into the formula to get the y-coordinate. Great. So A is the same A that we have in our form here. So A equals 1. That's my stretching factor. So we can graph this. We know where the vertex is. It's at minus 2, 1. And there's no stretching factor, and so it opens up. And these 2 points, the other 2 special points, at a height of 2 because it's not been stretched. So there's our graph. And we can write it in standard form now as x plus 2 squared plus 1. So when we don't have to complete the square because we can now figure out we know what the vertex is. So what are all the solutions to this equation? This parabola has no x-intercepts because it doesn't cross the x-axis, right? So that's fine. But what does the quadratic formula give us for this? So negative b, we'll just write it out again, b squared minus 4ac all over 2a equals minus 4 plus or minus the square root of 16 minus 4 times 1 times 5 all over 2 times 1. So it's minus 4 plus or minus the square root of 16 minus 20 all over 2, or x equals minus 2, well, minus 4 over 2 plus or minus the square root of minus 4 over 2. Negative number inside a square root. What do we do with that? Generally, when we're thinking about square roots, we want to think about them as negative numbers don't have square roots. Technically, though, mathematicians gotten around that by introducing something called I, and I is the square root of minus 1. And that gives us something called complex numbers. They're very useful in a lot of different places. Right now, for this class, we're just going to be keeping track of what kind of roots and x-intercepts we have. So how does it work? Well, minus square root of minus 49, that's I squared. Oh, square root of minus 49 is, let me undo that a little bit, minus 1 times 49. And so I'm going to abuse notation a little bit here and say this is this. Square root of minus 1 is I. Square root of 49 is 7. So square root of minus 24, same thing. It's minus 1 times 24. We take the square root of the whole thing, break that to minus I times square root of 24. square root of minus 1 times square root of 24. So that becomes I times square root of 24. So we deal with the minus sign essentially by bringing it outside as an I. So a complex number then is a number of the form a plus ib, where these two things are real numbers. And to find the conjugate of the complex number, just change the sign on the term with the I. So here's, so the conjugate is a minus ib. Complex numbers, you can add them, subtract them by combining like terms. That's very straightforward. What about multiplication and division? Multiplication is just FOILing things out. And I like to use the box method, and so I'm going to use that here. So when I multiply this out, what do I get? That's an I. I get a 3, I get a 2i, and then minus I times 3 is a minus 3i. 2i times minus I is minus 2i squared. So what does that give me? I get a 3. I can combine these two terms because they're like terms. This is a minus I. Right? That's these two terms added together. And then I have minus 2i squared. But I squared equals minus 1. Right? So this becomes 3 minus I, that's these two terms, and then minus 2 times minus 1, that becomes 3 minus I plus 2, or 5 minus I. Right? So when we're multiplying them, we can multiply it out. Just remember that the I squared turns into a minus 1, and then you can combine it with the first term. How to deal with a division is we're actually going to multiply the top and bottom by the conjugate of the bottom, right? And oops, parentheses like that. And the conjugate is just change the sign on the term with the I. So 1 minus 2i, the conjugate of this is out 1 plus 2i. You'll see why that's very useful in a second. So we get first is 1 times 3. Outer is 3 times 2i, so that's a plus 6i. Inner is I times 1, so that's a plus I. And then outer is I times 2i, which is a plus 2i squared. Underneath, you get first is 1. Outer is a plus 2i. Inner is a minus 2i times 1, so that's a minus 2i. And last is minus 2i times plus 2i, so it becomes a minus 4i squared. And this is why we multiply by the conjugate. These two terms cancel out. So what does that give me in the top? I have a 3 plus 7i plus 2i squared. And on the bottom, I have a 1 minus 4i squared. And now I'm going to use this fact again. 3 plus 7i, I squared is minus 1, so this becomes a minus 2. I squared is minus 1, so this becomes a 1 plus 4 in the bottom. And what do we have? 3 minus 2 is 1 plus 7i over 5, and we can break that into two pieces. And there's our division. And it's nicely written as a plus bi, which is the form we want our complex numbers in. So we ended up here with minus 2 plus or minus square root of minus 4 over 2. And now we can simplify that. We get minus 2 plus or minus 1 times 4 square root over 2, which is minus 2 plus or minus I times 2 over 2, or minus 2 plus or minus I. So we have no x-intercepts. Because the solutions to the quadratic equation, and we use the quadratic equation to find x-intercepts, right? They're complex. They're not on the x-axis. So no x-intercepts. Why are these always conjugate pairs? Remember that The quadratic formula is this. If b squared minus 4ac is negative, that means we get a complex number. There's no x-intercepts, but we have a plus or minus there. So you get one with a plus sign and one with a minus sign. So complex solutions to quadratic equations always come as conjugate pairs, 2 plus I and 2 minus I. The only difference between the two of them is that one's plus and one's minus. Okay, so factoring, we will stop this lecture here, and then we will pick up with factoring in a second.